Okay. Hello. Today I will be going through the F equals to MA 2025 problem 3. So the question reads as follows. So the context goes like this. Three identical disks are placed on a frictionless table. Initially, two of the disks are at rest. Third disk is launched with the speed v directly towards the midpoint of the two stationary disks along a path perpendicular to the line connecting their centers, as shown in the diagram below. Analyze the motion after the collision, assuming all interactions are perfectly elastic and that when the disks collide, there is no friction or inelastic energy loss. So this is the context of the problem. However, the third problem itself specifically reads, given this context, assume that there is a little imperfection in the disk's alignment so that when the disks collide, two collisions happen one at a time rather than simultaneously. And don't worry, if you don't understand what that means, I'll explain that in a minute. What is the final speed of the third disk? So what does this line mean? Assume that there's a little imperfection in the disk's alignment so that when the disks collide, two collisions happen one at a time rather than simultaneously. Well, it means something like this. Think about it, if you have your three disks all lined up in an equilateral triangle, it won't be an exact equilateral triangle because think of it, maybe one of the sphere disks has a little bit of an indent in it, causing the equilateral triangle to be somewhat squished together and somewhat skewed toward one side. However, this is so minimal that it doesn't really affect the shape of the formation when the three disks finally collide. So let's launch into the problem. Okay. So first, let's analyze so before we go into this problem, there's one really important concept that we should review. Okay, so think about it. How does a collision affect the components of the collision? So what I mean by this is that, think about it, if a ball is moving diagonally, okay, and it ends up hitting another object, how you might be wondering, how does the velocity of the original ball transfer to the velocity of the other ball with which it collides with? So we can analyze that here. So let's say there is a ball of mass m1 moving in a linear path with an original velocity of u, and it is heading in the direction of another ball with mass m2 and an initial velocity of 0, so it's in a rest. However, when it collides with the other ball, the ball of mass m1 has a new velocity of v1, and the ball of mass m2 gains a velocity of v2. So we want to find the relationship between u, v1, and v2 without anything to do with m1 or m2. So first we can apply the law of conservation of momentum. The law of conservation of momentum states that the momentum among a system of bodies will always remain the same, assuming it's a perfectly elastic collision. What is an elastic collision? An elastic collision is a collision such that no energy is lost when the collision is made. And in this case, the disks mentioned do have an elastic collision, so we can apply this principle in our problem that we are going to see today. So what we get is that our original momentum's sum of the momentum in the system is m1 times u, as that's the momentum of the first body, plus 0, as that's the momentum of the second body. After the collision happens, though, the momentum of the first body becomes m1 times v1, as now its new velocity is v1, but its momentum still remains the same, and the other body's momentum becomes m2v2 as it now gains some velocity, and therefore it has a non-zero momentum. So we get this first equation shown here. Now, but this won't be enough to gain an entire relationship between u, v1, and v2, right? No. That's where the law of conservation of energy comes into play. The law of conservation of energy states that energy will remain the same in the system. So what we did here is that we analyzed the kinetic energy of both of these bodies. So when the body starts to move, it has an original kinetic energy of half m1 times u squared. What does this mean? This means that the kinetic energy of any body would be equal to half of its mass times its velocity squared. And since the conservation of energy is maintained here, the kinetic energy of m1 plus the kinetic energy of m2 in this system will always remain constant. Meanwhile, while we know what the kinetic energy of m1 is, we also need to find the kinetic energy of m2. As the body is not moving, its velocity is 0 and hence its kinetic energy is also 0. Meanwhile, after the collision, the velocity of the first body becomes v1, so its kinetic energy becomes half m1 v1 squared, and then since the kinetic energy of m2 changes, as its velocity changes, it becomes half m2 v2 squared. So this simplifies into this equation m1u squared plus equals to m1 v1 squared plus m2 v2 squared. However, if we do some algebraic manipulation, we get that m1 times u minus v1 times u plus v1 equals to m2 v2 squared. However, we can analyze this equation a little bit further, right? We recognize this term m1 u minus v1 from earlier. Where do we see it? Law of conservation of momentum, that's where we see it. If we take this term to the other side, we get that m1 times u minus v1 equals to m2 times v2, meaning we can replace this term with m2 times v2. When we do so, we get m2 v2 times u plus v1 equals to m2 v2 squared, implying that u plus v1 equals to v2. This is an interesting fact because now this gives us the relationship between the three velocities. However, let's look at our own problem. Our own problem states that since these three disks are all identical, that means their masses must be identical as well, right? So that means in this case, m1 is equal to m2. So what happens when m1 is equal to m2? Let's find out. When we plug in that m1 is equal to m2, the first equation becomes m1 u plus 0 equals to m1 v1 plus m2 v2, but m2 is nothing but m1. So we can plug that in, giving us the equation that u equals to v1 plus v2. How does both this equation and this equation both apply, though, in the same case? The only way this is possible is that if v1 is 0. So essentially, if m1 equals to m2, and m1 is starting with an initial mass of u, when m1 collides with the other body, which in this case also has the same mass as it, all of its momentum will be transferred to the other body, so it will come to a rest position while the other body starts to move. How can we apply this in our problem? So let's look at our problem. Remember that so I'll be referring to the circle that is colliding with the two other circles as S3, S1, and S2. So over here. Okay. So think about it. When S3 is moving with a velocity of v, it has two components, v cosine 30 and v sine 60. That's sine 30. Okay? So the v cosine 30 will be the component with which it is colliding with S1. But remember what we just said, S3 and S1 have the same mass. So that means this entire v cosine 30 component, its velocity will be completely given to S1. So now we don't have that component anymore. And the only thing we're left with is this v sine 30 component in the 60-degree direction from the horizontal. So, and this is what we're going with to see our other disk, which is S2. So let's look at our diagram here. Our v sine 30 component is going at a 60-degree angle, as seen here. And as this is a near equilateral triangle, but not quite an equilateral triangle, the angles here will be 30 and 60, as if we look at an equilateral triangle, we see that a bisector will have a length of 30 degrees. And in this case, even though the spheres have imperfections, the imperfections are so small that it doesn't really make a difference to the actual shape of the figure when completed. So therefore, these angles are pretty much 30 and 60 anyway. The difference would be so small. Okay, anyway, back to our analysis of S3 and S2 collision. As S3 is moving at a V sine 30 component with an angle of 60 degrees to the horizontal, and the angle at which the joining of the centers is with the horizontal is 30 degrees, we get the following figure. V sine 30 itself has two components, the V sine 30 cosine 30 component, from which S3 is traveling to S2, meaning again, since S3 and S2 have the same mass, this component is going to be completely given to the S2, and S3 loses this bit of velocity. And the only thing it's really left with is this V sine 30 sine 30 in the 120 degree direction from the horizontal. So that should be where it's moving after the two collisions are made. And therefore, if we analyze the magnitude of this vector, we get that V sine 30 times sine 30 is the same as V times half, which equals to V over 4. And indeed, that is the correct answer. Thank you.